welcome back to another episode of the Dr. Perkins Podcast. Today we'll be discussing calories. So the critical thinking question today is we often heard that in terms of weight, a calorie is a calorie. Is that true? What are some things that would make you think that it's not true? So feel free to take a pause for some critical thinking. Once you think you know the answer, hit the play button, and I will tell you what I think is going on. So first off, what is a calorie and how do we measure them? Well, this beautiful picture was done by Ashalt Gul, and you can find that on Wikipedia's Creative Commons. And this is a bomb calorimeter. So one of the things that it does is we take food and we basically burn it, and we see how much the temperature goes up by. And so 1 liter of water, if you raise that temperature by 1 degree Celsius, it took 1 calorie to do that, right? And so if we got your sub from Subway in there, or French fries from McDonald's, whatever, when we burn it, and we raise that water temperature, let's say we have a liter of water in there, we raise that temperature by 10 degrees Celsius, that's 18 degrees Fahrenheit, we say that food has 10 calories in it. Now that being said, we're not eating our food and turning it to ash, right? Our body kind of metabolizes things a little bit different there. And so we can't just use this direct method here. We actually have to use some assumptions. So for example, fiber. We subtract fiber out of the mix because fiber is basically a sugar your body cannot digest, right? And so there are some assumptions going in here. Now, a lot of places don't use this thing directly. You can use chemical tests where you figure out how much protein's in your food, how many carbs, how much fat, and so on, and alcohol, but that costs a lot of money, so a lot of places don't do that. Instead, what a lot of places do is they would do what I would do. They would say, hey, look, I know that my cookies, I made it with 1 cup of sugar. All right, well, how much is that sugar? How many calories are in a cup of sugar? Oh, look at that. This table says there are, making stuff up for the sake of argument, 100 calories in my cup of sugar. All right. And then I used a cup of flour. How many calories are in a cup of flour? And so that's how most of your calorie comments come from. So, we got assumptions there. All medicine is based off assumptions. All science is based off of assumptions. And so if these are good assumptions, you get good medicine and good science. If it's bad assumptions, you get bad medicine and bad science. So let's see how this thing goes. So here's one of the molecules that are in our food, glucose. And so one of the things is we break down glucose through a couple of different steps. So the first step is glycolysis, and one of the things you're going to do is you're going to produce 2 ATP into NADH. Now I'm going to convert everything over into one measurement, particularly ATP. And so 1 NADH is equal to 3 ATP. And so at this step right here, we've created pretty much 8 ATP. We've stored 8 ATP worth of energy. And wait a minute, Dr. Perkins, I remember learning about glycolysis. They said that first step produced 2 ATP. Yes, 2 ATP were created out and out. But we have 6 ATP stored in this form of NADH. Now, if you don't have any oxygen, this gets wasted. But if we do have oxygen, we actually send this down to the mitochondria where they suck the energy off that NADH, and that's where we're getting an additional 6 pretty much ATP from. So the reason why I'm putting it like this is it's going to become very important when I compare this to fat or protein. All right. So next step what we got is pyruvic acid oxidation, and so we suck 2 NADH off of that pyruvic acid. Well, that pyruvic acid has the equivalent of 3 ATP worth of energy stored into it. And so once we send this down to the mitochondria, we're getting about 3 ATP per cycle. But, remember when we go through glycolysis, you don't produce 1 pyruvate, you produce 2 pyruvate for every single glucose molecule. So that's a total of 6 ATP per glucose molecule here. Now the next thing you got is the Krebs cycles, and once again this is running twice per glucose molecule, and so that's going to produce pretty much a total of 24 ATP right there. And so when we add these up, we get a total of 38 ATP. Now different places will tell you different things for how much ATP is in a glucose molecule. I've seen it as low as 29, and I've seen on the upper end like what I got here at 38 ATP. So where it really kind of gets a little fuzzy at is how many ATP are in this NADH and that FADH. It's not quite as clear. So anyways, we're going to just stick to using the 3 ATP for NADH and 2 ATP for FADH or FAD. Alright, so here is your citric acid cycle. And so, as you can see, this thing is going around and around in a circle, and it's sucking energy out of our food. And this wonderful picture was made by Naransi, and he put this up on Wikipedia for public use. So, wonderful person there. I appreciate his good work. Now, one of the big things is here are your different amino acids. Your proteins are made up of amino acids, so they're going to enter the cycle at different phases of the cycle. And so some are going to enter it high up here, others are going to enter it a lot lower down in the cycle, and so you're going to have a lot less energy left in this thing. Okay, so using the previous slide, we're going to kind of break down how much energy we're getting out of our amino acids here. Alright guys, so going back to that slide made by Narayansi at the Wikipedia, one of the things is I highlighted in yellow the steps where these different amino acids are entering in the cycle, right? And then I underlined in red the energy that was being sucked out at these steps. And so one of the things you can do is you can figure out how much energy is left in this molecule by the time it gets over here, right? When we get to oxaloacetate, we can't suck up any more energy. We got to put some more acetyl-CoA in it to redo this thing. And so the citric acid cycle, we get 2 turns for every 1 glucose molecule, right? So we have 2 pyruvates being made for every 1 glucose. And so we're going to put these 2 amino acids in at each of these steps and figure out how much energy we're going to get out of it. Okay, so this is how much energy is going to be in those molecules for where they're entering the cycle at. So remember, we need 2 amino acids to make the cycle go around twice, just like what we would see with glucose. Alright, so if we enter in at pyruvate, we're going to get about 30 ATP. Well, there's a problem here, right? Your amino acids can't just bing, magically turn into pyruvate. We actually have to spend some energy, because when we turn the amino acids into pyruvate, we produce a waste product called ammonia. Well, that's very toxic to the brain, and so we actually turn that into urea, and that's going to cost us 6 ATP. Some of that's going to be in the form of NAD and so on, but it's easily going to cost us 6 ATP there. So our energy yield went from 30 ATP to roughly 24 ATP. All right, and so let's just kind of go through these numbers real fast. We got this 24 ATP, but here's the thing. Our protein, our 2 amino acids weighed 220 daltons, right? So if I wanted to know who was a better employee, and I gave somebody $220, and I gave somebody $180 to do a particular job, it's not going to be the fairest contest here, right? Things are going to be weighted towards that employee that got the most money, the $220, right, to do that project. They had a $220 budget. So what we're doing over here is we're going to make the budget the same. That glucose molecule weighs 180 daltons. That's a measure of how much that molecule weighs. Those 2 amino acids on average are going to weigh 220 daltons. And so of course you'd expect it to have more energy because it's a bigger molecule. So we're just going to make things nice and equal. And so we're going to talk about the same amount of weight. So 180 Daltons worth of protein versus 180 Daltons of glucose. Which is going to give us more sugar? Which is going to give us more energy? Is it going to be the sugar or is it going to be the protein? And so, if our proteins become pyruvic acid right here, we're only going to get about 20 ATP worth of energy out of it. For the same amount of weight, that would have given us easily 34 to more liberal estimates 38 ATP worth of glucose right here. So if we enter at acetyl-CoA, we're only getting a net of 15 ATP. All right, alpha-ketoglutarate, we're only getting a net of 10. Succinyl-CoA, a net of 5. Fumarate, a net of 0. And oxaloacetate, we're actually losing energy, about 5 ATP, for the same amount of weight that we'd expect in a glucose molecule. Now, fortunately for us, most of our amino acids are going to be these entering at these 3 points, and it's going to be roughly equal. So if we use the middle number right here, we're only getting about 15 ATP for enough amino acids to equal 1 glucose molecule in terms of weight. Put another way, you're only getting about 39% of the energy that you'd expect to get from a glucose molecule. Now that's not what the bomb calorimeter says. The bomb calorimeter says, look, if you burn sugar and turn it to ash, or you burn protein and you turn it to ash, we're going to get just as much energy out of that molecule. But you can clearly see from these calculations, that's not what's happening here. Well, what about fat? So this wonderful picture, this is palmitic acid. This was made by Gento and Ben Mills, and they uploaded this on Wikipedia for the public domain. Anyways, what's going to happen is our fat, we're going to put 2 ATP in it, and then we're going to be able to run it through the Krebs cycle, also known as the citric acid cycle, until this thing is all gone. We're going to break off 2 of these carbon atoms every single cycle that we turn this thing around, until literally we've used up this entire molecule. Anyways, that's going to give us a net of 129 ATP. Well, the big thing is this molecule is a lot bigger than sugar. Sugar weighs 180 Daltons. So imagine I gave somebody $180 for a project, and they had about a $38 per month return. I gave somebody else $256 to do a project, and they came up with a $129 per month return. Well, which one is the better use of my money? Well, I mean, I'm making a lot more money per month with the $256 project, but I spent more money for that $256 project. So when you correct it for its size and say, hey, look, I'm going to decrease that, or we're going to pretend that we're only getting 180 Daltons, you're getting roughly 90 ATP per molecule for 180 Daltons worth of fat molecule. Anyways, that's going to give us about 2.4 times the amount of energy, which is pretty close to what the bomb calorimeter said, right? Bomb calorimeter said about 2.3. So when it comes to the energy content of the food being able to be used for fat and carbs, it seems pretty equal there. What the bomb calorimeter tells us is roughly what our body is able to use. But when it comes to protein, no, the bomb calorimeter really isn't that helpful there, because it doesn't take into effect getting rid of that energy in terms of the ammonia and stuff like that. Then on top of that, right, we're not even considering the hormone effects as well. As I said, your carbs are going to produce the most amount of insulin, followed by your protein, followed by your fat. The fat is going to produce the least amount of insulin and so on. All right. So some of you guys are like, well, that's a lot of fancy math and everything else, but where can you prove this in terms of clinical, right? I want some clinical observations here. So here's some clinical observations that should kind of give us pause, a reason to pause for that calories to calorie right here. So one of the things, United States, if you go on a diet in the long term, we're talking about 1 year or more, according to Ohio State University, you got about a 95% chance of failing. And what do we mean by failing? Well, your chance of weighing as much as what you do now or more in 1 year from now is about 95%. You only have a 5%, a 5 out of 100 chance of actually weighing less than what you do right now. According to the American Heart Association, 100 calories of trans fat is going to have a much different effect on your heart than 100 calories of cis fat, right? And so this wonderful picture right here, this came from Wikipedia with Miguel Ferrig. And so right here is your cis fats. So you notice the hydrogens are on the same side. Your trans fats, they're on opposite sides. This is what we blame for heart attack and stroke. Oh my goodness, don't eat this. This is going to kill you. This, we say, yes, eat this. This is really good. This is going to really reduce your risk of heart attack and stroke. If we have all the same atoms connected to all the same other atoms, but what's happening is one of them, the hydrogens are on the same side, and the other, the hydrogens are on the opposite side. This has a dramatically different effect on your heart, don't you think? And they're both fats. They're both, fats with double bonds. Don't you think whether or not you're eating a protein or a carbohydrate will probably have a dramatically different effect on your waistline? Alright. Another thing they did was the Minnesota starvation study. A lot of times what's pointed out, or what people assume, is that your BMR, that's your base metabolic rate, that's how many calories you burn if you're just laying in bed all day, is going to be the same. Whether you're dieting, whether you're eating, protein or fat or whatever. And so one of the things is when they put these people on these studies, they lost about 25% of the body weight. So if your BMR is static, pound per pound, right, it's not going to change, then you'd expect the BMR to have dropped by about 25%, right? You weigh 25% less, so you should be burning 25% fewer calories. But that's not what happened. The BMR dropped by about 40%. 40%, right? And put another way, compared to somebody that weighed as much as what they did at the end of the study, their BMR was 20% lower than that person, right? And so you can really see that what you're eating is affecting your BMR right there. Now, was that because of the severe caloric restriction, right? They really cut back on how much they were allowed to eat. And so they were only eating 1,560 calories per day, about half, and they kept cutting back further and further how much they were allowed to eat during this 6-month period of time to get them to that quarter weight loss. But their diet was basically potatoes, rutabagas, turnips, bread, and macaroni, right? Was it because of the diet they were placed on in terms of what they were eating? Or was it because of the lack of calories? I don't know. One thing I can foresee and understand is it seems like a pound of protein has only 40% of the calories that a pound of sugar would have in it, right? And then on top of that, your body doesn't want you to starve to death. And so I can see the body being set up that, hey, look, I don't have enough calories to do everything. Do I really need a blood pressure of 120/80? Do I really need a body temperature of 98.6? And so the body would make cuts in several areas. So how much of it is due to the body making cuts to try to save energy versus the body not needing to spend as much energy processing the food because of the type of diet you have? I don't know. But I suspect it is some of both. All right. Here's another thing. So, based off this idea that a calorie is a calorie, um, you know, one of the things we've targeted is fat in the diet, right? You want to be on a low-fat diet because, pound per pound, fat has twice as many calories in it as sugar does or protein does. And so the fancy name for sugar is carbohydrates. Because we have many different types of sugars. We got one molecule sugars, two molecule sugars, and three or more molecule sugars, but we'll save that for another day. But based off the assumption that a calorie is a calorie, look at the outcome. Americans have gotten way more obese, particularly severely obese. And so you can see obesity has tripled since the 1970s, and this is age adjusted. And the rate of severe obesity has gone up by a factor of 11 almost. And so I really like this graph because it is age adjusted, right? Young people are thinner than old people. So is obesity happening because people are getting older? Well, that would be a fair argument. But this graph, it standardized that. So we're looking at all the 18-year-olds. We put them in one group. All the 19-year-olds, put them in another group. And even when you hold the age the same, Americans are 3 times more likely to be obese and almost 11 times more likely to be severely obese. And so here's a great graph of America's consumption of sugar over time. And so you can see as the sugar consumption has gone up, obesity has gone up pretty much in lockstep right here. Now, it looks like following this down somewhere between 1995 and 2000, there's kind of a break here. And so the sugar is going down, but what's gone up at that same time? Artificial sweeteners. All right. And so I think this is very key. So what happens when you eat sugar? Well, your body releases insulin. If you want somebody to gain weight, put them on insulin, they'll gain weight. They did a study with type 1 diabetics and they put them on insulin, and even though they ate fewer calories, they still gained weight, and it was a significant weight gain. And so any food that causes you to release insulin will probably make you gain weight right there. And so the food that's going to trigger you to produce the most insulin is sugar, followed by protein, and then the least one is going to be fat. And so right here, this part of the graph makes a lot of sense right here. So what about over here at this part of the graph, right? The sugar consumption is going down, but the fat rate of obesity is going up. All right. Well, one of the things is artificial sweeteners. We'll pick on aspartame because one of the things PubMed has found is that when they give people aspartame, they actually feel hunger. They feel more hungry than if we gave them glucose. Well, what they're hungry, or if we give them straight water, right? What happens if you give somebody, make somebody hungry? Well, they're going to eat. Well, what happens if you eat too much? You gain weight. And so, unfortunately, a pretty good study showing that, look, we got a problem here. They also did another study that they found that people that had PubMed, there was another study that people that ate or drank lots of artificial sweeteners actually had more weight gain than those who did not drink artificial sweeteners. So I think a calorie is a calorie. It just isn't so. Maybe in terms of heating up water, but not in terms of controlling your waistline. So, all right, that concludes today's episode. If you liked what you heard, be sure to click the subscribe and like button down below. And as always, if you have any questions, comments, concerns, or if there's any particular topic you'd like me to create a video on, let me know in the comments down below. All right, well, I look forward to seeing you on my next podcast.